Okay, good. Good morning. My name is Sašo Džeroski, and I will talk today about semi-supervised and active learning, and in particular, the multi-target prediction for material design. This is joint work with Cynthia, who is here at this workshop, and two other colleagues, Jurica Levatic and Uroš Hribar. So just to get clear on the terminology, the tasks we are dealing with are predictive modeling tasks where we want to predict some target properties from some features, input features. So this might be properties of the material based on, let's say, process synthesis parameters or structural properties of materials or things like that. And if we want to predict binary or discrete values, we are talking about classification. If we want to predict continuous values, we are talking about regression. Okay. And in multi-target prediction, we want to predict several properties at the same time. So this is nothing unusual in material science. We typically want to predict at the same time, let's say, conductivity, band gap, all sorts of properties. So in this context, multi-target classification and multi-target regression can come in handy. And here's an example in collaboration with our material scientists from the Jožef Stefan Institute in Ljubljana. This is a multidisciplinary institute. It has both computer science departments and material science departments. And at one of these departments, they are looking at foamed glasses. And on the left-hand side, we have a list of parameters describing the process of synthesizing or foaming the glass. And on the right-hand side, we have the material properties that they are interested in, well, first measuring, but then also predicting for new and untried combinations. Okay, and here we have an example of a decision tree for multi-target prediction. Here in particular, we are predicting two properties at the same time, which are apparent density and an open porosity. And in each of the leaves of these decision trees, we get predictions for both of these properties at the same time. And the internal nodes in the decision trees contain tests on the values, in this particular case, of the process synthesis parameters. Now, when we are talking about semi-supervised learning, it comes in handy when we have relatively small numbers of data points. And in material science, this is not unusual. We typically have a handful or maybe dozens of samples that have been synthesized and characterized, and we would still like to learn from these. And in this context, semi-supervised learning is useful because it can handle not only labeled data with measured values of the target properties, but also unlabeled data where the values of the target properties are not known. And here in these tables, these are denoted by question marks. Okay. And the primary topic of this workshop has been active learning. So I would like to emphasize at this point the similarities and differences between semi-supervised and active learning. The similarity is that they both may make use of unlabeled data in addition to labeled data. The difference is actually semi-supervised learning is more incapacitated. It has to use the unlabeled data as is. It cannot ask, oh, you know, I really think this example would be nice to have a label on, so please go and label it. Semi-supervised learning cannot do this, while active learning can do precisely that. From the unlabeled examples available, it can go and handpick and say, aha, this one would help me learn a better model, so please label this, synthesize the material, measure its properties. So in our foam glass examples, unlabeled data would refer to foam glass samples that may or may have not been synthesized, but in any rate, their properties have not been measured. So we do not have the labels on the examples. Active learning could ask for property measurements for some of the foam glass samples, and if they have not been synthesized before, also for the synthesis therefore. Okay, and of course, I already mentioned earlier multi-target prediction. I mentioned semi-supervised learning. So here we are operating at the intersection of these two paradigms because we want to predict multiple properties simultaneously, and at the same time, we have some unlabeled examples. The table here at the bottom of the slide illustrates this notion, which is a bit more complicated in the multi-target case. In the single target case, you can just have a value or a question mark. So if I just go here, so for the target, it's either a question mark or a known label. But in the multi-target case, we have a more complicated situation. We can have a label completely missing. So this means for all of the targets, we have question marks, but we can also have partially labeled examples. And this means that for some of the targets, we have measured the values, but for others, we don't. And this is a bit more complicated than just completely present or completely missing labels. And we should be able to handle this as well to squeeze the maximum out of the available data. And so returning to our example task of predicting the properties of foam glasses, here in particular, we again have a semi-supervised learning task. The data samples, there is 165 of them. And for all of these, of course, the parameters of the glass foaming process were known. And some of the properties are measured for all of these. But for 41 of the 165 samples, actually some of the measured values are missing, and in particular for closed and open porosities. And this is unlabeled data that we would also, or partially labeled data to be very precise, and we want to exploit and use this data in the learning process. And of course, we would also like to know whether it helps or not. So the basic rationale behind semi-supervised learning is that using this unlabeled data in addition to the labeled one would help you achieve better performance. Now, there is a number of approaches to semi-supervised learning, and I do not have the time to go into the details of those, but we have in this particular case used two approaches to semi-supervised learning. The one is actually relatively general and can be wrapped around any learning method, and it's called self-training. So essentially, given unlabeled and labeled data, we build a predictive model on the labeled data only. Then we make predictions on the unlabeled data with the model we just learned. And very importantly, we estimate the reliability of the predictions of the learned model on the unlabeled data. And so where the learned model is most confident, we then say, oh, these are very confident. So we now take these to be labeled data. We move them from the unlabeled to the labeled part. And then we reconstruct a new model and we iterate until some stopping condition is met. And in particular here, we have wrapped this learning process around ensembles of predictive clustering trees for multi-target prediction, which I will explain on the next few slides. But even more simply, we can actually adapt this approach of predictive clustering trees for multi-target prediction in a very elegant way to take the unlabeled data into account. So this relatively complicated and iterative process is replaced with a single direct one-shot process of learning a tree by taking both the labeled and unlabeled data into account. So here is roughly how it works. First, let me explain these predictive clustering trees, which can be used for predicting multiple targets at the same time. The general process of learning decision trees is first to check for a stopping criterion, whether all of the examples we have are relatively homogeneous in terms of the target values. That is, they have low variance of the target values. And in that case, we construct a leaf and we label it with the prototypes, the averages of the targets. So this is the boundary condition. The iterative process or recursive process is that the data are not homogeneous. Then we look for a test in the features that are available. We look for a test to split the data into more homogeneous parts. So what we really want to do is we want to reduce the variance of the target. In the normal decision tree induction is just one target. Let's say it's one continuous variable, and we want to reduce the variance of that continuous variable. So that variance is the usual notion of variance of a continuous random variable. Now, what we have done with these predictive clustering trees is to generalize this notion of variance, not to work on only one target, but to work on multiple targets at the same time. And it is not really a new notion because this notion is already used in clustering. So this is the notion of intra-cluster variance from clustering. We want to split the data into subsets where this variance is lowered. But now this variance across all of the variables of interest. And then once we choose a test, we call this process recursively, and so the tree is constructed. So this intra-cluster variance function is shown on the slide. It's really sum of squared distances between each of the samples and the prototype or the average. And as I mentioned here, we have the freedom to actually choose the variables along which we studied this variance. So in standard clustering, this variance is assessed across all of the dimensions. In single target prediction, a single dimension. In multi-target prediction, across the target dimensions. Okay? And very easily you can imagine that if you have a number of continuous targets, you simply sum up their variances, and this is then your new variance function which you are trying to reduce. Now, this variance function can very elegantly be reformulated to include variances not only along the targets, but also along the inputs. Okay, so the standard part where we have a number of y's or target variables is this part here, which sums var of the y's, y1 to yt, going through the I index. And so this is the part of the targets. This is focusing on the prediction. But the red part actually is also looking at the variances of the inputs. Okay, so it's trying at the same time to find clusters which are homogeneous in both the input and the output variables. Of course, there is this W threshold with which we can put, let's say, less emphasis on the inputs. Excellent. And more emphasis on the targets, and we tune this with internal cross validation. And the nice things are that also we can then build ensembles of such trees. Now, returning to our example of foamed glasses, we have been trying here again to predict 5 properties at the same time. Here only binary low and high values. And we can see very clearly that semi-supervised learning improves performance. This is area under the precision recall curve averaged across the 5 targets. And you can see that if we are in fully supervised mode, we have area of 0.47 or 0.55, whereas we go to the 0.63 or 0.6667 range if we use the 40 partially labeled examples in addition to the fully labeled ones. And also actually the feature importances that result from the ensembles can change if we take the unlabeled data into account, which is very visible in this slide. Okay, so to summarize, we have applied semi-supervised methods for multi-target prediction to a real-world material science task, and we have improved the predictive performance, both for the case where we used self-training and for the case where we use this elegant generalization of decision trees. And this ties very nicely to active learning, although we have not done active learning so far. But you will remember in self-training, a key notion is this notion of the reliability of the predictions, which at a certain stage are deemed to be labeled. Now, in active learning, we can precisely ask to check actually the properties of those examples. And in this case, we can really move them to the labeled ones with confidence, with full confidence, rather than kind of making the assumption that they are fully labeled. And with this, I would like to thank you very much for your attention.
Yes, thank you very much, Sašo, for the nice talk. Is there questions in the audience?
Garrett, please go ahead.
Yeah, thank you very much for the talk. You had some really remarkable improvements in the quality of the models there. So a couple of questions. Would you be able to comment, please, on the computational cost of training and evaluating one of your predictive clustering trees versus a usual tree?
In general, this is very, very low. The only problems that we run into is when we have very, very high dimensional input spaces. Because in the semi-supervised learning case, they become part of the output space as well. So there we need to be a bit more careful. And in fact, Cynthia is working on a nice solution for this to reduce the dimensionality of the input space. And for the clustering part on the target side, use this reduced dimensional space, which still preserves the information, let's say PCA, autoencoders, these kind of things.
Cool. And secondly, mathematical question now, when you were adding the two variances together, so I was a little bit concerned that the quantities might have different units and then you can't formally add.
True, we do need to take care of that. So we do need to normalize per variable. And if you have discrete variables, you might be using entropy or Gini indices and whatnot. So you need to rescale that to the same scale. Also, something to take care of is to rescale where the outputs are missing or where the inputs are missing. You need to rescale the variance of the known part to the entire example. So if you have 5 variables in the input, 5 variables in the output, they're all on the same scale. If the outputs are known, you need to kind of multiply by 2 the variance of the known part.
Yeah, thank you for a nice talk. My question is, if I understood it right, these variances is taking into account much more the linearity of the problem. What if I would have very nonlinear problem? Would it work
linearity
as
well? is not an issue. The decision tree paradigm is approximating nonlinear functions with piecewise linear functions. And then 3 ensembles on top of that can model very nonlinear decision boundaries. So these properties still remain also in the multi-target case, also in the semi-supervised case.
Okay, thank you.
Thank you.
Do we have more questions in the audience? And no questions online, right? Yeah. So okay, so this was the last talk before the panel discussion, and are we fetching coffee before? And then yeah, let's fetch some coffee, and then we will be back in 5 minutes.